Good morning. Let us begin. We pick up from lecture 15, and since there has been a little bit of a gap, let me just quickly summarize where we are and the topics that we will be covering in today's lecture. Today we plan to introduce probably one of the most important concepts of multi-rate signal processing, that is in the context of the use of the DFT for spectral analysis. So that is an important concept, it is an important application, so something that definitely I would like you to pay close attention to. Of course, there are several flavors of applications to multi-rate, and what we will be doing is just touching upon a few of them, and in today's lecture and tomorrow's lecture, time permitting, we will look at some elements of the multi-rate and the techniques that we have developed. But basically we are going to introduce filter banks, and one of the manifestations or applications of filter banks is in spectral analysis, and that is what we will be looking at in today's lecture. So let me start by a quick question so that you can think about and give me an answer. Supposing I have the following setup. I have upsampling by a factor of 3, a delay z power minus k, and downsampling by a factor of 3. Okay, upsampling, downsampling by a factor of 3, and where k can be 0, 1 or 2. The output is, if k equal to 0, upsampling, downsampling cancel each other. So this will be equal to the identity system with gain 1 for k equal to 0. So that is equal to a gain of 0 for k equal to 1, and you can also verify that for k equal to 2 is also going to be the same case. So the general extension of this result is actually a very important result in multi-rate. If this is upsampling by m and this is z minus k and this is downsampling by a factor of 3, then and I am not specifying that k has to be equal to 0 to m minus 1. In the general case, what is this equal to? This is equal to a unity gain system for well, not strictly unity gain, it will either be unity gain or it will be z power minus k itself. Okay, no, let me make it as two separate cases so that we do not have confusion. So take the case where k equal to 0, 1 all the way to m minus 1. So then this becomes a unity gain term for k equal to 0, it becomes 0 for all others. Okay. So it is actually this sort of a structure actually eliminates a lot of the combinations that are possible. Now what happens if k equal to m, if z is equal to minus m? It will be the same as, how would you prove that? You can move the decimator to the left, then it will be, so this should not be 3, this should be m. So if this is m, so if you had z power minus m upsampling by a factor of m, downsampling by a factor of m, in that case then what we get is z power minus 1 as the delayed element. So any multiple of m is also okay for k, but it will come out to be z power minus k over m if k equal to multiple of m equal to 0 otherwise. Okay. So I hope the reasoning is clear and you are able to follow the. So where does this actually get applied? Usually these questions are not just out of the blue, there is actually an application for that. So, very often when you do in multirate, we do encounter situations where the upsampling and downsampling are by the same factor. Okay. Now, when you do sampling rate conversion, they will always be different, but in normal multirate applications, input and output sampling rate invariably will be the same. So, you can visualize the situation as follows. So, I have upsampling by a factor of 3, just as one of the operations I want to filter it by h of z and then downsample by a factor of 3. Okay. And this is more to test the application of the principle that we have just now developed. And I suggest that we do a polyphase decomposition of h of z, E naught of z cubed plus z inverse E1 of z cubed plus z minus 2 E2 of z cubed. And just as a suggestion, I say that okay, do the polyphase decomposition for the downsampler. Okay. Because for the upsampler you would have done type 2 polyphase decomposition. So, this is a type 1 polyphase decomposition for the downsampler. Okay. Now, given the result that we have just discussed previously, I would like you to think about the following structure. We have upsampling by a factor of 3, and I have done the polyphase decomposition. I have moved the downsampler to the far left. Then I have downsampling by a factor of 3, polyphase decomposition of type 1, Z inverse, downsampling by a factor of 3, Z inverse, downsampling by a factor of 3, and this one is E naught of z. It is no longer E naught of z cube because I applied the noble identity. Please draw the arrows so that we do not have any confusion. The second branch is E1 of z. The third branch is E2 of z, and all of these will get added up. Am I right? Okay. Draw the arrows so that there is no confusion about which way are going, which are the nodes which are adders and which are the nodes which are the ones where the signal gets split. Okay. So, what have we done? We have taken our downsampling part, applied the polyphase decomposition and obtained the polyphase implemented structure, and of course, the upsampling still remains. Now, if you focus in on this portion of the circuit and apply the result that we just now discussed, where you have upsampling, some delay, downsampling, how will you simplify this structure? Upsampling by 3, downsampling by 3, it is a gain of 1. With delay of minus 1, that branch is 0. Delay of minus 2, that branch is 0. So, this is identically equal to E naught of z. Okay. I hope you are able to see the simplification and how we have used the result that we have just obtained. So, the result was upsampling by a factor of m, z power minus m, downsampling by a factor of m, or z power minus k in the general case, invariably will come out to be a gain of 1 for one of the case, or for some cases, and it will be 0 for the others, and we can always exploit that when we have the multirate structures, and I hope you can see one of the advantages of this particular result that we have shown. Okay. Let us move on to the topics of today. Let me just quickly mention the two key points. L equal to lecture 14, the key result was the noble identities, but we must add a qualifier that blocks obtained after applying the noble identities must be realizable. They cannot be undefined blocks. Obtained after applying noble identities must be realizable or must be defined. can't get things like z power half and those things which we cannot define in a DSP context must be defined. Okay, keep that picture in mind, so that way we do not get unrealizable systems and then actually get into results or conclusions that are not correct. We have two types of polyphase decomposition. Usually the type 1 polyphase decomposition associated with the downsampling or with the analysis filters. Remember, we talked about when a signal gets split, that is called the analysis filters. So usually type 1 is associated with the analysis filters, type 2 is associated with the synthesis filters. Again, we will see several cases of these, and then it will become familiar with that. In the last lecture, we introduced the notion of filter banks, and we said that we would like to get several filters which span the range from 0 to 2 pi, and in that context we showed that there are types of filter banks. If the adjacent filters have some overlap, that is the most traditional or most commonly encountered. Occasionally you may want them to be non-overlapping, or you may want them to have significant amount of overlap. Both of these are possible, and based on the application you may design it as follows. Let me just answer one of the questions that came up after class, and that probably will answer questions maybe others also are having. Okay. Now, supposing I had a filter H naught which has the following form: minus pi over m to pi over m. Okay. Now, by modulating the impulse response with a cosine function, you can actually get a filter whose response looks like this. Let us say we modulate it by cosine 2 pi over m times n. Let us say you just want to use the, so then what will happen, you will get two copies of the spectrum. Basically you will do modulation, this will be 2 pi over m, there will be a copy of the spectrum at minus 2 pi over m. So this is obtained by using, so this is a case where the impulse response is real. So impulse response, if the original filter had real impulse response will still remain real, because you have done obtained the new impulse response by multiplying by a cosine function. Impulse response is real. Okay. On the other hand, the method that we talked about was using a modulation which was e power j 2 pi over n times n, and that gave us a different setup where you basically got a single spectrum. It was not plus and minus, there was only one centered at 2 pi over m. Okay. Now, there is a difference between these two. Which of these are we talking about, and why are we talking about one and not the other? If you look at the top line, where you take the filter multiplied by cosine 2 pi over m, then what happens is that the derived filter has got twice the bandwidth of the original filter. So it does not satisfy the uniform criterion. So this is a case where it becomes non-uniform, because one of your filters, the prototype or the basic low pass filter, has got a certain bandwidth, all of the derived filters have twice the bandwidth. Of course, there is no problem with that, but it does not satisfy the requirements of uniform. Whereas when you do the multiplication by e power j 2 pi over n, the complex exponential, then we actually get the case of uniform. Now, if you insist that no, I do not want to have to deal with, by the way, these have impulse responses that are complex even if the original impulse response was real. So here you find that the impulse response is complex. Okay. Now, if for any reason you prefer or you want to constrain your impulse response to be real, and you want to have uniform, it is possible. In that case, you will have two basic filters, one of them with the green type, the other one will be minus pi over 2m to pi over 2m, half the bandwidth. And Now what we will do is you will have the basic filter going from minus pi over m to pi over m, that means the total bandwidth of 2 pi over m. The derived filters will be derived from not by modulating the original the basic filter, but by the auxiliary filter. So what you will get is filters of this type. So you will still have the bandwidth of 2 pi over m. You can, the next filter would be of this type and so on. The colors show the pairs. Okay. So k equal to 0 is your basic filter, that came from a different set. All of the derived filters or the modulated filters came from a prototype filter which was half the bandwidth, and of course you would satisfy this condition. Again, there are applications where this type are, however our focus is not this. We want to have uniform, but we do not mind having complex responses. So therefore the uniform filter bank that we are talking about has the following structure. If it is an m channel filter bank, that means the range from 0 to 2 pi will be divided into m filters of equal bandwidth, and they are obtained by the shifts by the using the complex exponential. M channel filter bank. And this turns out to be a very interesting and a very rich area, and we will spend quite a bit of time studying and analyzing this particular case. But before that, one more time we will look at the notion of complexity reduction using the polyphase decomposition. Again, so we would look at the case of a fractional sampling rate change, fractional sampling rate conversion. Okay. And again, think through with me, and even if you do not have to draw write down everything, this particular thing is more for you to engage with the discussion points being presented. So I have the scenario of upsampling by a factor of 2 h of z, which will be my interpolation filter. It will also serve as my anti-aliasing filter, and downsampling by a factor of 3. Okay, it is a 2 by 3 rate conversion, and of course the anti-aliasing filter requirements will dominate. So this will be more like an anti-aliasing filter because it will be cut off with the pi over 3 as my. So now observation number 1. I know that if I do polyphase decomposition, I will get a factor of reduction in terms of computational complexity. If I combine it with this side, I will get a 3x complexity reduction, because that is what I get when I do the polyphase decomposition, and then I do that. Of course, if I do it this way, I will get a 2x, right. Now the question is, I am a little bit greedy, I want 6x. I want to get, why not ask the question that can you give me a structure that does 6x, and this is a classic problem, and you will say, well, just now we spent a lot of time, that you remember this delays, once these delays are present, you cannot shift the polyphase component, the downsampler and upsampler up. So let us take a quick look at what is possible in this structure. So step 1, okay, step 1, and again I will leave several steps for you to complete, but here is where, so actually I am going to combine it with the upsampling by a factor of 2. So the upsampling by a factor of 2, remember I said we will do type 2 polyphase decomposition whenever you are doing the upsampling. So it is R naught of Z upsampled by a factor of 2, a delay element, and the lower branch is R1 of Z upsampled by a factor of 2. You add these two signals, and then there will be a downsampling by a factor of 3. Okay, please draw the arrows. These are the polyphase decomposition of order 2. So there is R naught and R1. So polyphase decomposition is done for the filter H of Z into 2 polyphase components, and we get this structure. Okay. Now, the goal is if I want to get a factor of 6, that means the decimator has to move all the way to the left. So, let us take 2 cases. Let us take the case where you take the lower branch as step 2 and then you take the upper branch as step 3. Okay. So, step 2 is straightforward. Let me just request you to fill in the details of step 2. Step 2 is I have R1 of Z followed by upsampling by a factor of 2, downsampling by a factor of 3. Okay. I want to get maximum computational advantage. Upsampling by a factor of 2, downsampling by a factor of 3 can be interchanged, they are relatively prime, and then I have a filter R1 followed by downsampler, which means that I can do polyphase decomposition, move the downsampler all the way to the other end and get the factor of 6 advantage for the lower branch. Okay. Now, upper branch is when we may have to spend a little bit of effort, but again it is interesting, it is just a way of thinking about it, and the upper branch is step 3. Step 3. Okay. Step 3 says the structure that we have to simplify and apply to. So, 6x is obtained for here. Okay. I will assume you are able to convince yourself for the lower branch 6x is obtained. Upper branch, it is R naught of Z, R naught of Z followed by a upsampling by a factor of 2, Z inverse downsample by a factor of 3. Okay, that is the upper branch. Now, if both had been by the same factor, then the answer would have been 0, but of course they are upsampling by 2 and downsampling by 3, so that result does not help us. Now, the problem is, now we know that the upsampling and downsampling are LTI are time variant systems, and Z inverse is an LTI block. We cannot shift these things around, actually it will mess up, and I cannot even apply the noble identities because I know that I cannot get any unrealizable blocks in that. Okay. Now, is there any way to simplify? Is there any way that you see that we could basically I want a factor of 6 gain, which means that the downsampling by a factor of 3 must move all the way to the left. Upsample by 2, no I am sorry, upsample by 6, okay, but then you have downsample by 3, Z inverse downsample by 3, that will not help. Okay, think about this, Z inverse is the same as Z squared times Z power minus 3. So, then what you do is you swap these two around. So, rewriting it, what you should eventually get is you get Z up front, R naught of Z downsample by a factor of 3, then upsample by a factor of 2 times Z inverse. If you can get to this point, then of course you can get another factor, already we got a factor of 2. So, you can get the factor of 3 savings and get the factor of 6. So, this particular result, particularly if L and M are relatively prime, what is that result called? It is called Chinese remainder theorem, look it up. Okay. So, basically any integer can be written as a combination, a linear combination of 2 primes, and this is referred to as Chinese remainder theorem. Again our goal is not the mathematical aspects of it, there are some basically it is a very well known result. So, we will just use that, Z inverse is simple enough that we do not have to work too hard to get it, Chinese remainder theorem. Of course, there are several other applications where this actually comes into. So, this structure, if you do this, you will get the factor of 6x. So, the lower branch also gets a 6x advantage, and we will put a tick on that. So, overall you did get a 6x. So, that is a very good question. So, if you have upsample by L, downsample by M, they are relatively prime, only then they will be you will be able to interchange them. Then these delays, if they are in the range 0 to m minus 1, let us say, the Chinese remainder theorem says that I can always write it as a combination of some multiple of L and some multiple of M, and you will always be able to interchange. That is a very good question. Yes. So, do try it for three branches. I am sure it will be interesting to see. So, in fact, you can try that if you did the downsampling first. Then you can actually do the try it out. You will get z power 0, z power minus 1 and z power minus 2. You will get all the 3 terms.